We have the transformation given by A equals the vector with row 1, 0 and row 1, 1. And I've indicated that matrix right here, and here, and here. You'll see why. And we're trying to map the vectors 1, 0, this one, 1, 1, this one, and 0, 1, this one, as well as the 0, 0 vector, to see what happens to the unit square. Well, we take the matrix and multiply it by the vector 1, 0, coded in yellow here and yellow down here, and it's very clear that we get 1, 1. So we get the vector 1, 1, and that vector is right here. Okay, then we do the same thing to the vector 1, 1, the blue vector here, coded in blue here, and we get the vector 1, 2, which is here, directly above the tip of the vector 1, 1. You find the tip of the vector 1, 2. And then the vector 0, 1 maps on to itself, it turns out. So we get this. So that the unit square, if we go around this way here, we go around this way here on this parallelogram. Now, this is called shearing transformation. The idea simply being that this transformation takes the x-coordinate of any vector onto itself. So whatever the x-coordinate of your original vector is, that's going to be the x-coordinate of your transformed vector. So we have zeros here, we have ones here, we have ones here. On the other hand, the second row gives you the y-coordinate, and it adds the x-coordinate to the y-coordinate. So the y-coordinate becomes the x-coordinate plus the y-coordinate. We could even write the transformation in function form. T applied to x, y is the vector x, x plus y. And that leaves the x component of any vector unchanged, so that the x components of this vector and this vector are both 1, and the x components of both of these vectors are 1. The x component of this vector is 0, and the x component of the image vector is 0. The y component of each vector is the x plus the y component of the original vector. Okay, now the only vector that has both an x and a y component, to where you can see that, is the vector 1, 1. But this transformation takes 1, 1 onto 1, 2. So 1, 1, x is 1, we get 1. But x plus y is 1 plus 1, which is 2. So the x component stays the same, but the y component, or the y component gets bigger by whatever the original x component was. And I'm not sure I said that before, but again, I'll repeat it. I'm not repeating it again because I haven't repeated it yet, but I'm going to repeat it. And repeat it correctly. The y-coordinate adds to the old y-coordinate the x-coordinate, okay? The old x-coordinate. So this has the effect of shearing. Your book does a pretty good job of showing you how that works. You want to think about how it works. Okay, well, now let's look at another transformation, and this transformation is also on the document. Transformation 1, 0, 0, negative 1. Their transformation given by this matrix. Okay, what does it do to each of these vectors? Well, it takes 1, 0 to 1, 0. You can verify this doing the matrix multiplication. It takes 1, 1 to 1, negative 1. Takes 0, 1 to 0, negative 1. Let's think about it. The x component is going to be unchanged every time the x component is the same after as it is before. The y component gets multiplied by negative 1. So, well, 0, 0 times negative 1, you still have 0, but 1 becomes negative 1, 1 becomes negative 1. If we sketch the images of these vectors, which are again color-coded, we get this picture. So our sense of rotation has been reversed, and of course the scale here is different than the scale here. All these vectors have the same magnitudes they had over here, but the y component of each vector goes to its negative, so that the vector 0, 1 goes to 0, negative 1. The y component reverses. The vector then gets reflected through the x-axis. The x component doesn't change, but the y component reverses sign. And the same happens to this vector. It goes down here, so we get this picture. Okay, well, what about transformation 1, 1, 0, 1? I'm not sure what this is about x doubles, y doubles. I am, but it doesn't have anything to do with this transformation. This is just a picture of the transformation. You can verify it. And what's happening here is very similar to what happened here, only it's the x coordinate that adds the old x coordinate, the original x coordinate, to the original y coordinate. And we get this picture, which is a whole lot like this one. It's just that x is being sheared instead of y. Okay, now we have another transformation. I think we have another transformation where x doubles and y doubles. Now this is our original scale. Okay, if this is our scale where this is 1 unit, then these vectors, this vector and this vector, have magnitudes of 2 units. We're doubling x, we're doubling y. And this is the result of that transformation. And the transformation for that, I don't know that I asked for it, but it's very simply 2, 0, 0, 2. That would be the matrix for the transformation that doubles x and doubles y. It should be obvious why that is. Okay. Another transformation, x doubles and we rotate 45 degrees. What's that do? Well, same thing here, but now we rotate 45 degrees. Now, 45-degree rotation, the matrix for the rotation is going to be, well, it's going to be cosine of 45 degrees, negative sine of 45 degrees in the first row. And then sine of 45 degrees, sine of 45 degrees, cosine of 45 degrees in the second row. Not sure that was requested, but that's straightforward. In this example, I actually tell you how the transformation works. Okay, a rotation through angle theta, and I don't have room to write through angle, well, maybe I do. Okay, rotation through angle theta would be cosine theta, negative sine theta, sine theta, cosine theta. It's fairly easy to prove that using a little bit of trigonometry in a picture. That negative is up here. I did that so it wouldn't look like I'm subtracting the sine of theta from the cosine of theta. And if it still looks like that, just look at this as a matrix with 4 entries, okay? A row of 2, a row of 2. Okay. The matrix that rotates 37 degrees, then you would plug 37 degrees in here. The matrix would be, now I gave you the values. Cosine of 37 degrees is approximately 0.8. Sine of 37 degrees is negative 0.6. And using that with this form, here's the matrix. And you can verify that multiplying this matrix by each of these vectors gives you something that looks very much like this. It doesn't change the length of any vector. It just rotates it by something very close to 37 degrees. The matrix for x doubles and y triples, what would that matrix look like? And what would the transformation look like? Well, here we've got x doubling. If this is the original length 1, this is length 2. And then x triples, or y triples, sorry, y fourples, okay? This is a picture where x doubles and y fourples. That's really quadruples, but fourples sound so much neater. Okay, so x doubles, and then if we double this, we get something like this. So there's a picture of the transformation for x doubles and y fourples. And I think maybe I ask you on the document for the transformation for x doubles and y triples. Well, that means that xy would transform to x doubles 2x, y triples 3y. What's the matrix for that transformation? Clearly 2, 0, 0, 3 is what you would multiply by xy in order to get 2x, 3y. Now there's one transformation that does something a little different. And it's the transformation given by this matrix. Okay, the matrix 1, 1, 1, 1. All the entries are the same. Well, clearly this matrix reduces to this, meaning that the rank of the matrix is 1. And the column space has dimension 1. Okay, column space is spanned by 1, 0, and the row space is spanned by the vector 1, 1. Column space is spanned by the vector corresponding to this leading 1, and that vector is 1, 1. Now if you apply this to each of these vectors, this is what you get. They're all in the same direction. And they would all be right on top of each other if I really put the initial point of each at the same point, at the origin. I don't want to draw them right on top of each other, then you can't tell one from the other. So I offset them just a little bit, but they're really intended to be one on top of the other. I mean, they represent one on top of the other. Okay? So what happens is this transformation collapses this square to just a line segment from here to here. Okay, all the vectors lie within this line segment. And the entire space here maps to a simple one-dimensional line. Okay? All multiples of any vector are going to be along this line. Okay? So again, I mentioned that the rank of this thing is 1. The dimension of the row space is 1. And the basis of the row space is the vector 1, 1. Should have written that as a row vector, but the basis of the column space is also 1, 1. Row vector 1, 1. This row vector is the basis for your row space, well, this row vector. And this column vector over here is the basis for your column space. They happen to be the same, but not for the same reason. Also have a kernel. Okay, the set of vectors that map onto 0. Well, if I augmented this matrix with a column of zeros, I would have the matrix that represents the condition that the transformation acting on the x vector gives us the 0 vector. That is, that the x vector maps to the 0 vector. And we've seen that already, so hopefully you understand what I'm talking about. Reduced, that would give us this matrix with still a row of zeros, because no row operation with a column of zeros here, because no row operation would change anything if our last column is change our last column. No row operation could change our last column if the last column had all zeros, because there wouldn't be anything but zeros to add to any other row. And multiplying by a row by 0 wouldn't change the fact that its last number is 0. So if you just write down the augmented matrix, reduce it, and see what it tells you that the xy maps to 0, 0 if and only if x plus y is 0. Okay? And you don't have any restriction at all from the second row. Okay, if x plus y equals 0, then x equals negative y. So whatever y is, x will be the negative of it. The result is that your kernel has a basis consisting of negative 1, 1. Now you could as easily say 1, negative 1, because any multiple of this basis vector is still a basis vector. You might want to think about that a little bit. So we have rank 1, nullity is 1, because the basis of the null space consists of one vector.